2,500 degrees Celsius. That's not a volcano. That's not a blast furnace. That's a chemical reaction you can start with a kitchen match, and today, someone used it to cook a steak. By the end of this video, you'll know exactly why this reaction is hot enough to melt steel in seconds, why it doesn't explode even though it looks like it should, why the genius plan to cook dinner with it fell apart in under 30 seconds, and the one overlooked chemistry detail that turned a perfectly good medium-rare steak into biohazard. Stick around, this gets worse before it gets delicious. Building the mystery before explaining the chemistry. Let's start with the plan, because on paper it's almost elegant. Take a flower pot. Line the bottom with a steak, fill the pot with a mixture of iron oxide, rust, essentially, and aluminum powder. Light it. Molten iron drains through the hole in the bottom of the pot directly onto the meat, searing it instantly from a reaction so hot it shouldn't even be survivable to stand near. It's the kind of idea that sounds insane until you realize it's built on real, well-documented chemistry. Chemistry that's been used for over a century to weld railroad tracks together in the middle of nowhere, with no electricity and no furnace, just powder and a spark. This reaction has a name, thermite. And here's the first myth we need to kill immediately, because almost everyone gets this wrong. Thermite is not an explosive. It doesn't detonate. There's no shockwave, no blast wave, nothing you'd see in an action movie. What thermite does is something arguably scarier. It burns, just unbelievably hot, and it cannot be put out with water. In fact, water makes it worse. We'll get to why. So somebody stood over a flower pot, packed with a reaction hot enough to liquefy iron with a steak sitting directly underneath the exit hole. What could possibly go wrong? Everything. Everything could go wrong. And it did, but not in the way you'd expect. Before we get to the collapse, the chaos, and the verdict on whether this steak was actually edible, we need to understand what's actually happening inside that pot at a molecular level, because once you see it, you'll never look at rust the same way again. The real chemistry, told like a heist. Here's the question nobody in that backyard was asking, but should have been. Why does mixing rust and aluminum powder release enough energy to melt steel? These are two solids. Neither one looks dangerous. You could hold both in your bare hands 5 minutes before ignition. The answer is a story about a very old grudge between oxygen and aluminum. Every element has what chemists call an affinity for oxygen, basically, how badly it wants to bond with it. Iron has some affinity for oxygen. That's literally what rust is. Iron slowly, losing an argument with the oxygen in the air over billions of collisions, one atom at a time, until you get iron oxide. But aluminum wants oxygen more, not a little more, dramatically more. If you measure it, and chemists have, exhaustively, the bond between aluminum and oxygen is significantly stronger energetically than the bond between iron and oxygen. That gap between how strongly iron holds onto oxygen and how strongly aluminum holds onto oxygen is not just a number in a textbook. That gap is energy. Real, physical, released heat energy. So when you mix iron oxide and aluminum powder and give it a spark, here's what actually happens. The aluminum atoms essentially rip the oxygen away from the iron atoms. Aluminum oxide forms completely stable, completely happy, and the iron, no longer needing to share electrons with oxygen, is dumped out as pure, molten metal. This is called a thermite reaction, technically an aluminothermic reaction, and it's a specific type of chemical process called an exothermic redox reaction. Redox meaning reduction and oxidation happening simultaneously. Iron is being reduced, stripped of its oxygen, while aluminum is being oxidized, gaining that oxygen. Exothermic meaning the whole process throws off enormous heat, because breaking the iron-oxygen bonds costs less energy than you get back from forming the aluminum-oxygen bonds. That leftover energy has nowhere to go but into the surroundings as heat and light, and we're not talking about a small amount of leftover energy. This is why thermite has been used industrially since the early 1900s. Welders would haul the thermite mixture out to remote rail lines with no power source available, ignite it in a ceramic crucible positioned over the broken rail joint, and let gravity and chemistry do what a blowtorch and a generator normally do. No plug required. No fuel tank, just two solids and one spark, releasing enough concentrated heat to melt and fuse steel rail on the spot. That's the reaction sitting in that flower pot. Not a fire, not really a flame in the way you'd think of a campfire. A self-sustaining, self-fueling chemical transfer of oxygen so violent in its energy release that it produces molten iron as a byproduct. The same molten iron that was supposed to drip through a hole and sear a piece of meat like the world's most dangerous kitchen appliance. Here's the part that should have set off alarm bells before ignition though. Once you light thermite, you cannot control it. There's no dial. There's no simmer setting. The reaction, once started, consumes itself at whatever rate the chemistry dictates, and the byproduct is a stream of liquid metal at a temperature that will burn straight through most containers people assume are heat-proof, including, as it turns out, a flower pot. Real-time tension. Now that we understand what's inside, let's rebuild the moment. The mixture is packed. The steak is positioned directly beneath the drainage hole, and somewhere around the half-minute mark, ignition happens. What you'd see, if you were standing at a safe distance, and you should be standing at a very safe distance, is not an explosion. It's almost the opposite, a controlled, blinding, white-hot burn that starts at the ignition point and spreads through the mixture like a wave. Sparks fly outward, not because the reaction is unstable, but because tiny droplets of molten iron and aluminum oxide are being ejected as gases, and trapped air pockets are heated instantly and expand. Within seconds, not minutes, seconds, the temperature at the reaction site rockets past the melting point of iron, which sits at roughly 1,538 degrees Celsius. Thermite reactions regularly exceed 2,500 degrees Celsius, which is hot enough to melt through, warp, or ignite almost anything nearby that isn't specifically engineered to survive it. And a terracotta flower pot was not engineered to survive it. This is the detail that makes the whole experiment such a perfect case study in what chemists call the difference between theoretical containment and material reality. On paper, the flower pot is just a vessel with a hole in the bottom, a funnel. In reality, it's a piece of fired clay, never designed to sit in direct contact with liquid metal at temperatures that exceed the melting point of the pot's own structure by a wide margin. Terracotta doesn't melt the way metal does. It doesn't have a clean liquid phase. Instead, at extreme, sudden heat, it does something worse for anyone relying on it to hold shape. It experiences thermal shock. The outside heats and expands far faster than the inside can keep up with. Internal stress builds beyond what the material can handle, and it fractures, sometimes catastrophically, sometimes just enough to fail structurally at exactly the wrong moment, which is exactly what happened here. Instead of the reaction burning cleanly through to completion and draining molten iron in a controlled stream through the intended hole, the entire structural integrity of the pot gave out first. The reaction had no dial, no simmer setting, no pause. Once ignited, thermite consumes itself until it's finished. There was no way to stop it mid-reaction. There was only one way this could go from here. Either the pot survived just long enough, or it didn't. The odds were never actually in the pot's favor. And within moments, physics made its final decision. The container was about to lose this fight completely. The pot's walls finally gave out under the stress. When a 2,500-degree reactions container fails, there's no mostly contained. The burning thermite mixture didn't drain through the hole anymore. It fell directly and violently onto the stake. This happened in less than a second, start to finish. Blink during the footage, and you'd miss the exact moment. Technically, the original goal was still happening in some form. Molten iron was still meeting the stake, just uncontrolled. Burning reactant, unreacted aluminum, and iron slag crashed down together. Instead of pure refined iron flowing cleanly, this was chaos. This moment reveals something important about the whole experiment. The chemistry itself performed exactly as the math predicted. Every prediction about bond energy and reaction temperature held true. What failed wasn't the science, it was the engineering. Specifically, it was the container wrapped around that science. The one variable that had nothing to do with chemistry. Everything came down to whether terracotta could survive contact. Contact with something 4 times hotter than its tolerance, it could not. And the collapse proved that instantly. This is exactly why industrial welders use ceramic crucibles, purpose-built vessels engineered specifically for this molten output. Swap that engineering for improvisation, and containers fail. And they don't fail gently, they fail all at once. So there it is, chaos, mid-experiment, caught on camera, burning material and molten slag dumped without any control. All of it landing directly onto raw, unprotected meat. The stake was never meant to receive the entire apparatus. Yet here it was, buried under a collapsing reaction. The obvious next question hangs in the air immediately. Was there anything salvageable left of the original plan? Could this possibly still produce anything resembling a cooked meal, or was the entire experiment simply over at this point? From the outside it looked like total unsalvageable failure. The stake was now buried under burning reactive material. Smoke, sparks, and molten slag obscured the original target. Nobody watching could have predicted what happened next, because the answer here genuinely defies expectations. This is where most viewers assume the story ends badly. It doesn't end the way you'd think it does. The disaster wasn't actually the end of the experiment. It was, unexpectedly, still delivering on part of its promise. Somewhere underneath that chaos, real cooking was still happening. The heat hadn't gone anywhere, it had simply lost its container. All that thermal energy still needed somewhere to go, and the stake was directly in its path. This detail matters more than the collapse itself, because it says something about how much energy thermite carries. Even total structural failure couldn't stop the heat transfer. What happened next surprised almost everyone who watched it. It's time to find out what was left of that stake. Despite total structural failure, the stake actually came out cooked, not burned to ash, not raw, genuinely, properly cooked. The finish was medium rare, exactly a deliberate sounding result. Let that sink in for a moment before moving on. Even in complete chaos, the reaction still delivered real heat, for enough time, to properly cook meat. Think about what that implies about the temperatures involved. Medium rare requires an internal temperature near 54 to 57 degrees. The reaction above it exceeded 2,500 degrees Celsius. That's not a small safety margin, that's absurd, thermal overkill. And it was delivered in a completely uncontrolled chaotic burst. yet it still cooked the steak to a precise finish. This reveals something important about thermodynamics and heat transfer. Heat doesn't need to be perfectly controlled to do its job. It needs to be present, close, and applied long enough. The reaction didn't need a clean drainage system to work. It needed raw thermal output, and Thermite has that in excess. So on a pure did it cook basis, this experiment worked. The physics of heat transfer didn't care that the pot failed. The steak got hot. The steak got properly done, which, on the surface, should have been the happy ending. A chaotic failure that somehow still achieved its core goal. A story about how even disaster can produce results. This is the kind of twist that makes chemistry fascinating. Predictable reactions producing unpredictable, almost comedic outcomes. The steak's doneness was, honestly, impressively accurate. Exactly the texture and color you'd want from good beef. It looked, from a distance, like a genuine cooking success. Anyone glancing at it might assume dinner was ready. But a closer look tells a very different story. Because cooked properly and safe to eat are not the same, that distinction is about to become the entire point. The collapse didn't just deliver heat to that steak. It delivered the entire reaction, physically, onto the surface. Solid aluminum oxide, unreacted metal particles, iron slag. All of it landed directly on the meat itself, not near it, not adjacent to it, directly on it, mixed into the sear, coating the entire exterior surface. This is where cooking chemistry becomes toxicology instead. And the answer here isn't ambiguous in the slightest. Aluminum oxide and iron slag are not food-safe substances. They're industrial byproducts of a metallurgical reaction, produced through processes never intended for human consumption. There's no reliable way to just scrape it off, especially once it's fused into a seared surface. Fused at temperatures exceeding 1,000 degrees Celsius. So the doneness of this steak stopped mattering entirely. Perfect texture didn't matter if the surface was contaminated. And the surface was, unmistakably, completely contaminated. Which brings us to the actual final verdict on dinner. The final verdict on this steak wasn't about doneness, it was about exactly what covered the entire surface. The steak was completely coated in thermite reaction residue. That single fact made it categorically inedible, regardless of cooking. This is arguably the most important lesson in the story. Cooking meat with thermite and eating it are different questions. Nobody seems to have considered that difference beforehand. The heat did exactly what heat is supposed to do. But heat wasn't the only thing that landed on that meat. Byproducts of a violent metallurgical reaction landed there too. And those byproducts don't disappear once cooking is finished. They remain physically fused into the food's surface. This isn't a matter of taste or presentation. It's a basic, non-negotiable food safety issue. Industrial reaction byproducts are never approved for consumption. They were never tested, certified, or intended for eating. No amount of good doneness changes that fact. A perfectly seared steak can still be completely inedible. This experiment proves that distinction in the clearest way possible. It's a reminder that cooked is not the same as safe. The chemistry, again, performed exactly as it should have. It reliably produced heat, molten metal, and reactive byproducts. All three of those things reached the steak simultaneously. Two of them cooked it, one of them ruined it. This is the core irony of the entire experiment. Technical success and practical failure happening at the same time. The steak looked like dinner and functioned like a warning. And this pattern isn't unique to backyard chemistry experiments. In any experiment, the weakest link usually isn't the reaction. Chemistry, understood properly, is remarkably predictable and consistent. It's the human engineering around the chemistry that fails. The container, the setup, the assumptions made beforehand. Here, that assumption was believing a flower pot could hold. That single assumption undid an otherwise correct chemical process. It's a small detail with enormous practical consequences, and it's exactly the kind of detail easy to overlook, especially when the underlying chemistry seems straightforward on paper. This steak became a case study in that exact mistake. Perfect chemistry paired with an imperfect real-world execution. The result, a scientifically successful, practically disastrous outcome. Nobody walked away from this with dinner on their plate. But everyone watching walked away with a genuine chemistry lesson. Sometimes the most memorable lessons come from total failure. This experiment earns its place for exactly that reason. It's chaotic, it's dramatic, and it's scientifically completely accurate. Every step of it can be explained through real chemistry. That combination is rare, and it's worth appreciating fully. The steak may have been ruined, but the lesson wasn't. And this experiment, remarkably, was only part of something bigger. There was a wider purpose behind this entire chaotic afternoon. This experiment wasn't just a stunt for its own sake. It was reportedly part of a larger project about iron. The whole point was exploring iron's chemistry hands-on, not through explanation alone, but through direct demonstration. Viewed that way, the steak becomes almost a side effect. The real question was always about iron itself. What actually is iron, chemically, and why does it matter? Iron is the fourth most abundant element in Earth's crust. It's central to some of civilization's biggest technological shifts. The entire Iron Age is literally named after this element. Access to strong, workable iron reshaped agriculture and warfare. It also reshaped construction and tools across entire societies. Iron isn't just historical, it's inside you right now. It's bound up in hemoglobin, inside your own blood. That iron carries oxygen through your entire circulatory system. Left alone with oxygen and moisture, iron slowly corrodes. That corrosion is the exact same iron oxide from earlier. There's something almost poetic about that complete chemical cycle. Iron ore gets refined into pure metal through huge effort. Left exposed, that same metal slowly oxidizes back into rust. Thermite uses aluminum's hunger for oxygen to reverse that process. It rips the oxygen back off in a matter of seconds. That returns the iron to a pure molten state instantly. It's the entire industrial history of iron, compressed dramatically, compressed into just a few seconds in one flower pot. Seen this way, the experiment isn't just a chaotic stunt. It's a visceral, memorable demonstration of a fundamental chemical fact. Iron's relationship with oxygen defines almost everything about it. Sometimes that relationship happens slowly, over years, as rust. Sometimes it happens violently, in seconds, as pure heat. Both are the exact same underlying chemistry at different speeds. That's a genuinely elegant idea hiding inside a messy experiment. It's easy to miss that elegance amid the chaos and smoke. But it's there, in every second of that reaction. This is why single experiments rarely tell the full story. They're most powerful as pieces of a bigger exploration. One reaction, one element, one small piece of a larger puzzle. And iron, it turns out, still has plenty left to reveal. Every rusted nail carries this exact same underlying chemistry. Every railroad weld relies on this exact same reaction. Every drop of your blood depends on this same element. From ancient tools to modern engineering, iron connects everything. This one chaotic experiment ties directly into all of it. That's what makes it worth understanding beyond the spectacle. The stake may be gone, but the lesson isn't. Real chemistry, told through a real messy human story. Not a lecture, but a demonstration with real consequences. That's ultimately what made this experiment worth exploring. And it's why this reaction still fascinates chemists today. Now, let's bring this whole story back to where it started. Let's return to that number from the very beginning. 2,500 degrees Celsius, the number that started this. That's the temperature this entire story revolves around. Hot enough to melt steel in a matter of seconds. Hot enough to cook a steak, even after total failure. Hot enough to make a flower pot a genuinely bad choice. What failed here was never actually the underlying science. Every prediction about the reaction held up completely. The redox chemistry between iron oxide and aluminum was flawless. What failed was everything wrapped around that chemistry. The container, the assumptions, the belief terracotta could survive it. Purpose-built crucibles exist specifically to withstand this exact output. A garden flower pot was never built for that job, and that single gap changed the entire outcome completely. This is really the lesson worth carrying away from all this. Understanding a reaction is only half of any real experiment. The other half is respecting what you don't control. Once you light the fuse, the chemistry takes over completely. There's no pause button, no adjustment, no second chance. That's true in a flower pot, and true in a lab. Chaotic experiments like this one make chemistry feel alive. They turn abstract concepts into something visceral and memorable. A bond energy diagram becomes a collapsing flower pot instead, and a steak nobody could actually eat becomes unforgettable. Iron still has plenty of secrets left to reveal. This was only one small chapter in a much bigger story. If chaotic, chemistry-driven experiments interest you, there's more coming. Real reactions, real failures, and real lessons hiding inside them. Because sometimes the best way to learn chemistry is watching it break, and this experiment broke in the most educational way possible.